90% of AI workloads will fail without Kubernetes in the next 18 months, and most teams have no idea why.
Wait, are you saying AI companies can't scale without Kubernetes infrastructure?
So we're covering why CNCF calls it foundational, the scaling bottlenecks, and what teams need to implement now?
By minute 4, you'll know exactly which Kubernetes features are non-negotiable for AI. Let's get into it.
Welcome to the Platform Engineering Playbook Daily Podcast. Today's news and a deep dive to help you stay ahead in platform engineering.
Today, we're diving into CNCF. Kubernetes is foundational infrastructure for AI.
Stick around to the end for this week's headlines. Let's dive right in.
So the CNCF just dropped their annual survey results, and here's what caught my eye. 82% of container users are running Kubernetes in production, and 66% of organizations are already using it to host their generative AI workloads. But Chris Aniszczyk made this really interesting point. He called Kubernetes foundational infrastructure for AI systems.
That's a pretty bold claim. I mean, when I think AI infrastructure, I'm thinking about GPU clusters, CUDA cores, tensor processing units.
Right. And that's exactly what makes this fascinating. The survey data shows something we haven't really talked about enough. There's this massive gap between training AI models and actually deploying them. Jonathan Bryce nailed it in the report when he said most enterprises aren't building or training their own models. They're consumers.
So we're talking about inference workloads, not training.
Exactly. And that changes everything about how we think about AI infrastructure. The survey shows 98% of organizations have adopted cloud-native technologies. That's not just adoption, that's basically universal acceptance. And when you combine that with the fact that 59% are using cloud-native for much or nearly all development.
Wait, hold up. Those are huge numbers. What's driving this?
The report breaks it down into 4 maturity levels: explorers at 8%, adopters at 32%, practitioners at 34%, and innovators at 25%. What's really telling is their North Star metric, GitOps adoption. 0% of explorers have implemented GitOps, but 58% of innovators are running GitOps-compliant deployments.
That's a massive spread. What about CI/CD?
Even more dramatic, 91% of mature organizations use CI/CD tools in production. And get this, 74% of innovators check in code multiple times per day. We're not talking about quarterly releases anymore. This is continuous deployment at scale.
Multiple times per day. That's insane velocity.
And here's where it gets really interesting for platform engineers. Application containers in production jumped from 41% in 2023 to 56% in 2025. But pilot-only deployments? Down to just 6%. Nobody's experimenting anymore. They're going straight to production.
That seems risky. What about testing?
That's the thing. When you have proper platform engineering practices in place, with GitOps, CI/CD, and containerization, you can move that fast safely. The platform becomes the safety net. But here's what really matters for our listeners. If Kubernetes is becoming the de facto platform for AI inference, what does that mean for platform teams?
Yeah, because AI workloads are fundamentally different from traditional microservices, right?
Completely different. We're talking about models that can be gigabytes in size, inference requests that need consistent sub-second latency, and resource requirements that can spike dramatically. And that's before we even get into things like model versioning, A/B testing different models, or handling GPU scheduling.
So platform teams need to evolve their Kubernetes expertise specifically for AI workloads.
Not just evolve, fundamentally rethink. Because if 66% of organizations are already doing this, and that number is only going up, this isn't a future trend. This is happening right now. Coming up, we'll dig into exactly how platform teams are adapting Kubernetes for AI workloads, including some surprising technical challenges that nobody saw coming.
So let's get into the technical weeds here. How exactly are organizations running AI inference on Kubernetes?
Great question. So first, let's talk about what inference actually looks like in production. You've got your model, could be a fine-tuned llama variant, could be a custom vision model, whatever. And it needs to be containerized, versioned, and deployed just like any other application.
But models aren't applications, they're massive binary blobs.
Exactly, and that's challenge number one. A typical microservice container might be 50 to 100 megabytes. An AI model container, we're talking 5 to 10 gigs easy. Some of the larger language models can push 20 to 30 gigs. That completely changes your deployment strategy.
Image pull times must be brutal.
Oh, they are. I've seen teams waiting 10, 15 minutes for model containers to pull on new nodes. That's why you're seeing solutions like model registries, separate from container registries, lazy loading techniques, and aggressive caching strategies. Some teams are even pre-warming nodes with common models.
What about the actual serving infrastructure?
This is where it gets really interesting. You've got projects like Kserve, that's the evolution of KF serving, which provides a standardized way to deploy models on Kubernetes. It handles things like auto-scaling based on inference requests, canary deployments for new model versions, and even multi-model serving on the same infrastructure.
Multi-model serving. How does that work?
So instead of dedicating resources to each model, you have a model server that can dynamically load and unload models based on requests. Think about it. If you've got 50 different models, but only 10 are actively being used at any given time, why keep all 50 in memory?
But wouldn't the loading time kill your latency?
It can, which is why you need intelligent caching and prediction. The platforms are getting smarter about this. They'll keep frequently used models hot, preload models based on historical patterns, and some even do speculative loading based on request patterns.
What about GPU scheduling? That's got to be complex.
Incredibly complex. Traditional Kubernetes scheduling assumes CPU and memory are your primary constraints. But with AI workloads, you're scheduling based on GPU availability, GPU memory, and even specific GPU types. An A100 isn't the same as a T4, and your model might perform differently on each.
How do you handle that heterogeneity?
Node selectors and taints are your friends, but it goes deeper. NVIDIA's GPU operator helps with driver management and GPU feature discovery. Then you've got tools like the NVIDIA GPU device plugin that makes GPUs visible to Kubernetes as schedulable resources. But here's the kicker. You also need to think about GPU sharing.
Sharing GPUs, that sounds like a recipe for resource contention.
It can be, but it's also necessary for cost efficiency. A single A100 can cost $15,000 plus. You can't dedicate one to a model that only gets a few requests per hour. So you've got technologies like NVIDIA MPS, multi-process service, or MIG, multi-instance GPU, that let you partition GPUs. Some teams are even doing time slicing.
What about the operational side? Monitoring, debugging, that sort of thing.
This is where platform engineering really shines. You need to monitor not just traditional metrics like CPU and memory, but also GPU utilization, model inference latency, token generation rates for LLMs, and even model drift detection. Tools like Prometheus with custom exporters, Grafana dashboards specifically for AI metrics, and distributed tracing for inference pipelines.
Model drift detection in production?
Absolutely critical. Your model performance can degrade over time as real-world data diverges from training data. Platform teams are building automated systems that monitor prediction confidence, track accuracy metrics, and even trigger retraining pipelines when drift is detected.
That sounds like a lot of additional complexity for platform teams.
It is, but here's the thing. The CNCF survey shows this is already happening at scale. 66% of organizations aren't planning to do this. They're doing it right now. And the ones who figure out how to do it well are going to have a massive competitive advantage.
What about cost optimization? Running AI workloads can't be cheap.
Cost is huge. We're seeing teams implement sophisticated scheduling strategies, spot instances for batch inference, reserved capacity for real-time serving, and even cross-region failover for cost optimization. Some teams are saving 60 to 70% on their AI infrastructure costs just through better scheduling and resource management.
Stick around, we'll give you the exact checklist for preparing your platform for AI workloads, including the critical decisions you need to make in the next 90 days.
First thing, audit your current Kubernetes setup. The fundamentals still matter. If you're not already at that practitioner or innovator level the CNCF talks about, meaning solid CI/CD, GitOps, monitoring, you need to get there first. You can't run before you walk.
Makes sense. What's the specific checklist for AI readiness?
Number 1, storage strategy. Traditional persistent volumes aren't going to cut it for multi-gigabyte models. You need high-performance storage that can handle large files, ideally with caching layers. Look at solutions like JuiceFS or even object storage with intelligent caching.
Object storage for models?
Absolutely. S3-compatible storage with local caching gives you the best of both worlds. Centralized model management with fast local access. Plus, it integrates naturally with model versioning strategies.
What about the GPU infrastructure?
Start small. You don't need A100s for every workload. For many inference tasks, T4s or even CPU-based inference might be sufficient. Build a decision matrix: model size, latency requirements, request volume. Use that to determine your GPU strategy. And definitely look at GPU sharing from day one. The cost savings are too significant to ignore.
Any specific tools platform teams should evaluate?
K-serve is almost mandatory at this point. It handles so much of the complexity around model serving. Ray is another one, great for distributed inference and scaling. For monitoring, look at tools like Arise or YLabs for model performance tracking. And don't forget about feature stores. Feast is a good open source option.
That's a lot of new tools. How do you prevent tool sprawl?
Great point. The key is to think in terms of capabilities, not tools. You need model serving, model monitoring, and model management. Whether that's 3 tools or one integrated platform depends on your needs. But don't try to bolt AI onto your existing microservices platform without modifications. It won't work.
What about the skills gap? This is pretty different from traditional platform engineering.
Huge challenge. You need people who understand both Kubernetes and ML operations. My advice, start with your strongest platform engineers and give them dedicated time to learn ML concepts. Pair them with data scientists. Create that bridge between the two worlds.
Cross-functional teams for platform engineering?
Exactly. The days of platform teams working in isolation are over. You need embedded ML engineers or at least regular collaboration, because the decisions you make at the platform level, like how you handle model versioning or GPU scheduling, directly impact model performance and data science productivity.
What should teams watch for in the next 12 to 18 months?
3 big trends. First, edge inference. As models get smaller and more efficient, we'll see more Kubernetes at the edge for AI workloads. Second, federated learning and privacy-preserving ML will drive new platform requirements. Third, the rise of specialized AI chips. Beyond just NVIDIA, think Google TPUs, AWS Inferentia, even Apple Silicon for inference.
How does that change platform strategy?
You need to build abstraction layers. Don't hard-code NVIDIA assumptions into your platform. Use device plugins, build vendor-agnostic interfaces. The teams that stay flexible will be able to adopt new hardware as it becomes available.
Last question. What's the biggest mistake you see teams making?
Treating AI workloads like stateless microservices. They're not. Models are stateful, they have warm-up times, they have specific hardware requirements. The second biggest mistake, underestimating the operational complexity. This isn't just about deploying models, it's about versioning, monitoring, updating, and optimizing them continuously.
So it's really about building a new operational muscle.
Exactly. And here's my closing thought. The CNCF survey shows 98% adoption of cloud-native technologies. In 5 years, I predict we'll see similar numbers for AI workloads on Kubernetes. The platform engineers who start building these capabilities now aren't just preparing for the future, they're positioning themselves at the center of their organization's AI strategy. And in a world where every company is becoming an AI company, that's an incredibly powerful place to be.
Platform engineering is the enabler of AI transformation? I like it.
It's not just about the technology. It's about democratizing AI within your organization. When any team can deploy and manage AI models as easily as they deploy microservices today, that's when the real transformation happens. And that's the opportunity for platform engineers, to be the ones who make that possible. Before we wrap up, let's catch up on this week's infrastructure news. There's a major incident we need to talk about. Cloudflare experienced a significant BGP route leak on January 22nd that impacted their network operations. According to their incident report, an automated routing policy configuration error caused them to leak border gateway protocol routes, which essentially means traffic that should have stayed within their network got advertised to the broader internet.
BGP incidents like this can cascade quickly across the internet. Did they share specifics about the scope of the impact?
The blog post indicates it was caught relatively quickly, but any BGP leak can potentially redirect traffic through unintended paths. For platform engineers, this is a stark reminder about the importance of automated policy validation. Even Cloudflare, with all their expertise, can fall victim to configuration automation gone wrong.
It's interesting they're being transparent about an automated system causing the issue. That takes some courage to admit.
Speaking of automation and modern infrastructure, the Linux Foundation just released a fascinating report showing how Kubernetes has become the de facto platform for AI workloads. But here's the kicker. They found that organizational culture is actually the biggest factor in successful AI adoption, not the technology itself.
That's a plot twist. Everyone's racing to adopt the latest AI tools, but culture is the bottleneck?
Exactly. The report highlights that while Kubernetes provides the scalability and orchestration needed for AI workloads, teams with strong collaboration practices and a culture of experimentation see far better outcomes. It's not just about having the right platform, it's about how your organization uses it.
This aligns with what we've been saying about platform engineering being as much about people as it is about technology.
Now, switching gears to something that might surprise our listeners, Google's Chromium project has published an extensive list of banned C++ features. This isn't just a style guide, it's a comprehensive breakdown of language features they've explicitly forbidden in their codebase.
Banned features in a modern C++ codebase? What are we talking about here? Go-to statements?
It goes way beyond that. They're restricting certain template metaprogramming techniques, specific standard library features, and even some abseil library components. The document explains that these restrictions help maintain code consistency and prevent common pitfalls in a codebase as massive as Chromium.
That's a sobering reminder that even with modern C++ improvements, large-scale projects still need guardrails. Platform teams working with C++ services should definitely review this list.
That wraps up this week's news. That's our show for today.
If you found this valuable, please subscribe and share with a friend who'd appreciate it.
Drop us a comment with your thoughts on today's topic.
Links to everything we discussed are in the show notes.
And check out platformengineeringplaybook.com for more resources and guides. Until next time.